You are. Thanks everyone for coming. The focus of my talk is going to be about performance. First, I'll start with Facebook NVIDIA partnership. Then I'll talk about the Caffe2 performance, and the most of the talk will be about the Volta, the latest NVIDIA GPU architecture, and how we implemented Volta in Caffe2, how we are implementing it, and at the end we will have some QA. So we have a very good relationship between the Caffe2 team at NVIDIA and Caffe2 team at Facebook. We have actually dedicated engineers working full-time on Caffe2 at NVIDIA. Caffe2 is a Facebook product, but at NVIDIA we treat it as if it was our product. So we have QA. So we have we have a serious QA process. As I said, we have dedicated engineers working on it. And because of this commitment, we had a pretty good contribution to Caffe2. We write a lot of tests, we run a lot of tests, we contributed to the build system, we try to use the latest deep learning SDK, CUDA, cuDNN, Nickel in Caffe2. We write new operators, we optimize the existing operators, we add features to the operators. So all of this contribution and the engineering work, development, building is done on a cluster that we made at NVIDIA just for the deep learning frameworks. It's a cluster of a bunch of DGX1 machines. We also use the supercomputer Saturn V. It's an infrastructure for us for building, testing, benchmarking. So this commitment and this tight relationship between the teams results in, you would expect it results in a good performance for Caffe2. So I have some numbers here for the performance. This is on DGX1 machines for Inception V3 and Resonant 50. These are very deep networks. And the main point of this slide is the scaling. As you can see, from 1 GPU to 8 GPUs, 1 GPU to 8 GPUs, we get a pretty good scaling. It's on Resonant 50 is about 7.7. And these numbers at the top of the bars are the number of images per second that processed during training these models. If you don't believe me, these numbers are great. You can compare Caffe2 with other frameworks. It's one of the fastest frameworks out there. So these are the Caffe, it's actually NVIDIA Caffe, Caffe2, TensorFlow, MXNet, Tor, CNTK, and Chainer. This one is Caffe2. So besides the good performance, Yangqi mentioned that it's a very flexible framework, and you can easily extend your models to pretty much a lot of different things if you want. So now, given the good performance that you saw, we all know that you can always do better. And because of that, we made Volta. Volta is the latest NVIDIA GPU architecture. It comes with a piece of hardware called Tensor Cores. The main thing about this hardware is that it can do matrix multiplications. So usually when you want to do arithmetic, you multiply two numbers and then you accumulate the results of multiple multiplications into a floating point number. But this hardware supports multiplying matrices, and it accumulates the results of the multiplication into another matrix. And this brings a lot of good performance. So as another outcome of this great partnership with Facebook, Caffe2 is one of the first deep learning frameworks that's getting Volta support. Of course, this work is still in progress, but Volta support essentially means having FP16 data type support throughout the framework and also a bunch of Volta-related optimizations. If you look at the recent commits on GitHub on Caffe2, you see a lot of Volta-related activities related to FP16. So I'm going to talk a lot about FP16. I would like to define what FP16 means actually. I'm sure all of you are familiar with floating point numbers or float. A float is a 32-bit number. It has 1 bit for the sign, 8 bits for the exponent, and 23 bits for the mantissa or fraction. And this is an example how it's represented. You multiply the mantissa by 2 to the power of the exponent, and you can represent a floating point number. So FP16 everything is the same except that you have fewer bits. Instead of 8 bits in the exponent, you have only 5 bits, and instead of 23 bits mantissa, you only have 10 bits. So why do we care so much about FP16? It comes with 4 benefits. So the first one is faster compute. If you have compute-bound operations in your model, like convolutions or fully connected, compute-bound means most of the time in doing these operations is taken by doing the arithmetic on the hardware. If you have such operations, doing FP16, having a hardware that supports doing FP16 arithmetic is better because hardware can usually do FP16 arithmetic faster. On the other hand, if you have a memory-bound operator, such as batch normalization or ReLU, where most of the time is taken by reading or writing data, then if you write your data in FP16, you can move the data faster, so better bandwidth. And the third one is is in a multi-GPU setting. When you have multiple GPUs, often these GPUs need to communicate data. For example, in a synchronous SGD algorithm, at the end of each iteration, GPUs need to communicate the gradients. So if you store these gradients in FP16, you have 2x smaller data. So you can communicate faster. These GPUs can communicate faster. And the last one is about memory. Of course, if you store data in FP16, you save memory by 2x. So, but all of these benefits don't come for free. There is a big challenge with FP16, which is the numerical range. Since you only have 5 bits for the exponent and fewer bits for the mantissa, you lose a lot of precision because of the mantissa. And also the range of the values, the range of the floating point numbers that you can represent is smaller. And then during the training, when you're training a model, if you have values that cannot be represented by an FP16, you're going to either see overflow where your number is too big, your floating point number is too big, therefore you cannot represent it, it becomes infinity, or you will see underflow, your number is very small that can't be represented in FP16. FP16 doesn't have enough precision, the number becomes 0. So this is a big challenge for FP16. At NVIDIA, we did a lot of research to resolve this problem, and we came up with a number of methods. I'm going to talk about 3 of these methods that we found. The first 2 ones, I'll talk about them briefly. The main one is the last one I'm going to focus on. The first one is gradient scaling. So as an example, gradients are numbers that tend to be very small. When you're training a model, In the backward pass, you generate the gradients. And these gradients are supposed to be used to update the parameters of your model. These gradients are usually very small values. In this histogram, you see that most of the gradients, these numbers on the x-axis are exponents of the floating point number. As you see, most of the gradients are very small. The exponent is, you don't have any exponent, any floating point with exponent larger than 0. So this area is where the FP16 can be used. Outside of this range, any value cannot be represented. So the values that are too small, such as all of these, 64% of your gradients are here. So all of them become 0. So this area is totally unused. So one simple method you would think of is to multiply all of these gradients by some fixed value to shift this range. Then you can later during the training, you can cancel out that multiplication, scale down your gradients by, for example, dividing your learning rate. When you're training your model, you can scale up your gradients by some value and scale down your learning rate to cancel out this scaling. That was the first method. The second method is about updating the weights. So if you store all of your gradients in FP16, and if you store all of your parameters in FP16 as well, then when you want to update the parameters using these FP16 gradients, the effect of these update, when you want to add the gradients to the updates, the effect is almost nothing. Because then the FP16 range is so small, the precision is low, you don't see any change when you add the gradients to the parameters. They don't change. So one idea is to store the weights in FP32 instead of FP16 in normal float. And then when you want to add the gradients, cast them up to FP32, multiply by gradients, add them to the parameters, and then work on the new parameters. So that is about the second method. Any questions so far? So the last one is about Volta. So when you have a multiplication, when you want to do arithmetic in hardware, you're doing a multiplication on two numbers. If these two numbers are in FP16, and then you put the result of that in another FP16 value, and you do the accumulation on that, you lose precision. We would like to do the multiplication in FP16, but store a result in an FP32 value so that we can do the accumulation on FP32. And that turns out to be very, very effective. And Volta exactly does that. That piece of hardware I talked about, Tensor Cores, not only it supports multiplying matrices, it also supports multiplying matrices that are stored in FP16, like each element in the matrix is an FP16 value, but also it supports doing the accumulation on an FP32 matrix. And that turns out to be very effective for accuracy. So this is the Tensor Core, the Volta Tensor Core. So you have two matrices stored in FP16. You do the multiplication, and then you do the accumulation on an FP32 matrix. And then the output is also FP32. So we trained a lot of different models at NVIDIA. We did a lot of research on models related to computer vision, language modeling, etc. And it turned out using these methods solve all of the problems. We can use either one of those methods, one of those three methods, or we can combine them in different ways. And then we get pretty much good accuracy for all of the models. This is for resonant 50. You can compare the accuracy of FP32 training and training on Volta Tensor Core, and the accuracy of both are pretty much the same. So Volta not only provides good performance, but also the accuracy, it keeps the accuracy of FP16 in a good shape. So this table pretty much describes the recipe for using Volta. If you want to use Volta and do accumulation, you do use Tensor Core for accumulation in FP32, and use the other methods that I talked about, this is a good recipe to use. You can store all of those activations and gradients in FP16. Again, the benefit is faster bandwidth, faster compute. But for parameters, only for convolution and fully connected that are compute bound, you can store you can keep 2 copies of the parameters, both in FP16 and FP32. But for the other ops, you use FP32. I'll talk about the 2 copies down here. And then for the math type, like what type do you use for the mathematics, for the arithmetic on your operators? Again, for convolution and fully connected, you use FP16. For others, you use FP32. For the regular training operators, such as learning rate, softmax, cross entropy, etc., use FP32 as usual. And then the last one is parameter updates. If you are, so first I briefly mentioned this in the previous slides. First, you cast up your gradients. Gradients are stored in FP16, right? As I mentioned there. You cast up your gradients to FP32, then you use the FP32 version of the gradients to update your weights, and then if you have a convolution of fully connected which has 2 copies of the parameters, you just cast down the result, the new weights to the FP16. So this recipe has worked for us for many different models, and now I'm going to talk about the performance of this. So now, FP16, how did we do it in Caffe2? Of course, this is work in progress still. Volta is not out there yet, and we are still implementing different pieces of FP16 in Caffe2. I'd like to start with some training script. This is a typical training script in Caffe2. If you want to train a model, your training script usually looks like this. It consists of 3 parts. The first part is for defining your model. The second part is for creating your model. And the last one for running your model, for training. So the first part, for defining the model, there is this API called Data Parallel Model Parallelized GPU. So a user that defines the model needs to only define these 3 functions. And then you give those functions to this, it defines the model for you. Once you do that, then you come here to create, to this line initializes the model, like all the variables that are needed, and then this one creates an instance of the model, and then you, in a loop, for whatever number of iterations you want, you just run the training. And during the training, you can fetch any metrics you want from your model. So the user only needs to define these 3 functions, and that's what I'm going to focus on now. The first one is generating data. You need to provide a function that says how you want to generate your data. The second one is for generating the net, like what operators you want to put on your model. And then the last one, how you want to update your parameters. First one is generating data. For computer vision, like ImageNet, if you want to do ImageNet, usually store your data in a database, and then there is this operator createDB that provides a reader, a database reader. You use that. But the main operator is this one, image input. Use this operator. It uses that database reader as an input, and it provides you data and label as the output. And then you put a bunch of arguments here, like batch size or data augmentation arguments if you want for your images. And that's basically the function that generates the data. Now, if you want to do FP16, meaning that you want an operator that reads the data and reads the data from disk and generates data and label in FP16, then you just need to add this argument to the function so that the output type of this operator becomes FP16. So the second one was generating the model. This is for a simple model. I think is MNIST, but no, it's actually CFAR. So you add a bunch of operators to your model, like convolution, max pooling, fully connected, ReLU, and fully connected. Each operator gets the output of the previous operator and uses that as the input. And then at the end, you use the output of the last operator for the softmax, and you generate the loss, and you return the loss. This defines the model for your training. Now, for FP16, you need an initializer for FP16 because we want to store the weights of convolution and fully connected in FP16. That's why we have to add that at the top, and then at the end, when this fully connected, the last one ends, you convert the FP16 values to FP32 because softmax needs to work on FP32 values. So there is this operator in Caffe2 called half to float. There is another one called float to half that you can use to cast up or cast down. And then this is gradient scale. This is the first method I was talking about. If you want to multiply all of your gradients by some fixed value, you can simply do it over here. You simply multiply the loss by gradient scale, which is some value like 256, for example. And by the chain rule, if you want to do the mathematics, by the chain rule, you can prove that multiplying the loss only can propagate this multiplication down to the other layers. And then the last function was parameter updates. You have to define a function that defines how you want to update your parameters. And this is very easy. If you want to add a weight decay, for example, you add this operator, but the main one is build SGD. You put your learning rate, the policy of learning rate, step size, and all the other parameters. And that does the parameter update for you. Now, if you want to do FP16, so first, there is this build multi-precision SGD you can use, and that does all the parameter update tricks that I was talking about, like casting up the gradients from FP16 to FP32, doing the update on FP32 values, and then casting down the FP32 values. That's all done in this function. And gradient scale here is to cancel out the multiplication that we did in the previous slide. You just divide your learning rate by gradient scale. So this was all about how you can do FP16 in Caffe2. I'm not sure how much time I have to talk about the backend implementation, probably not much. But I'd like to mention how we can enable Volta Tensor Core in deep learning frameworks, including Caffe2. This is done through cuDNN. So now cuDNN v7 is not out there yet. We have cuDNN v6. This is an example for convolution. There are Volta Tensor Core can be used for other operators such as fully connected, but this is only for convolution now. In cuDNN v6, if you want to do convolution, you have to create a convolution descriptor. The first line creates a convolution descriptor, and then you also have to set your convolution descriptor with a bunch of arguments that I don't, like stride, for example. What's the stride of your convolution? Now, in cuDNN v7, the API is going to look like this. Of course, it's not released yet. the exact form may change before the release, but it will be something like this. After you set the convolution descriptor, there is this new API called set convolution math type that you use this value from that enum. That enum is new. Once you set this, that would tell cuDNN to use Volta Tensor Core hardware. Otherwise, it will use the regular algorithms without using the new hardware in Volta. And then the other value of the enum is for the default. That means if you set that means it won't use the Volta Tensor Core. So about Volta performance, this is the resonant 50. I showed you the 8 GPU numbers in one of the earlier slides. 1784 number of images per second, that's what we get with DGX1. This is on 8 GPUs on Pascal. Then if we use Tensor Core, Volta Tensor Core, that's the speed up we get. So the values are, the activations, gradients are FP16, the parameters are FP32, except for convolution and fully connected, and all the arithmetic is done using Tensor Core. And the speed up is almost 2.4x. I think that's pretty much, yes. That was, if there is any question. Yes?
I'll be right there. So wanted to know the way we can add FP16 for P100. Is it possible for training?
We have done research. We have done research on that. It's harder because of the numerical problems. It's possible. There was actually a talk on GTC. I'm not sure if you attended GTC. There was a talk about that, about different like FP16 recipes for Pascal. Paulius is here. He can provide more information if there is.
Training with FP16 on Pascal. So I think, I guess the options would be, I think cuDNN has some APIs, right, to do FP16 convolutions and such, so that'd be an option there. One challenge with FP16 on Pascal is that accumulators FP16 are. So Pascal does have FP16 math instructions, or GP100 GPUs have it. The lower end ones do not. Well, they do, but the throughput is lower. So the challenge is a P16 accumulator, which is not as flexible as when you accumulate into, so what did I say? So Pascal accumulates into FP16, whereas Volta can accumulate into FP32. And we found that to make life quite a bit easier if you accumulate into FP32. But to do that today on Pascal, you can use cuDNN calls that support FP16. Also, for fully connected layers, you can use Let's call, I think it's GemEX call. You can configure FP16 math as well. You probably want to scale the gradients, and one way to do that is to scale the loss at the end, and then we'll move up all the gradients. That helps in some cases. In some cases, more work had to be done. So there's a bit more detail in the GTC presentation. I think also Boris Ginsburg gave a talk at NIPS last December on all kinds of presentation. So I guess brief answer is, yeah, there are cuDNN API calls and cuBLAS API calls that will do FP16 math underneath. So you have to resort to those, and you'll just have to pay more attention to your range. You probably want to shift the gradients, as one of the figures showed, that into the higher exposure range, just so we don't lose as many values to zeros and default.
So for Caffe2, there is no scene right now.
I guess Pooya is your best answer for Caffe2.
I believe you can. I've never tested that, honestly, but I believe you can.
Yeah, I just want to know if you plan to support it for Caffe2.
Yes, because you only need cuDNN v6, right?
Yeah.
Which is supported in Caffe2. you may, and we are adding FP16 support, like we are adding FP16 data type support throughout the framework. So once that's there, and you have Cudian and V6, you should be able to do FP16 in Pascal. Yeah. I should have introduced Paulius. Paulius is one of the researchers that worked on FP16 on Volta. He did great work. Any other question? Yes.
I'd like to ask a somewhat open-ended question. That well, you found that if we take an FP32 model and try to retrain an FP16, it requires special tricks to make it possible. But both FP32 layout and FP16 layouts, they were not created for neural networks specifically. Like this is something we endowed from like previous developments. So do you think that it's because of previous advances in neural networks that all neural networks before us and state-of-the-art neural networks were trained in FP32 that we have this problem? Or is it something like fundamental that like 10 bits precision is not enough, but without other tricks, but 23 bits is enough?
I don't think there is anything special about the number of bits in float, like 23 bits. I've actually heard that there are models that cannot work with float. You need double precision. It's very rare, but so it's clear that if you decrease the number of bits, you're going to lose precision, right? There might be models that don't work with FP16, but so far we have done training on all the popular models with computer vision and language modeling, and it seems working, FP16. I don't know. We may find some other models that can't work.
So I guess I just have another quick comment maybe. So when you go and look at FP32 versus FP16, there are sort of two components, right? So you have the exponent and you have the mantissa, right? So I guess your question was focusing more on mantissa, that you have 23 versus 10 bits. At least in our experience, and that was sort of demonstrated in Pooya's figure, more of a challenge was really the exponent, right? Because the figure he had, the x-axis for the histogram was really just the exponents, right? So mantissa is just going to, give you a different number of samples or a specific number of samples for a given exponent value. And the challenge that we had with FP16 is that a lot of values were in the range that's denormal for FP16 or not even representable in FP16, that they become zeros. Because if you look at FP16, exponent can be in the range between -14 and 15, if I remember that correctly. And denorms can extend that to -24. So in FP32, exponents can get as small as -127. So there you actually can represent many more smaller values that you cannot represent in FP16. And sort of the gradient scaling or loss scaling that we applied was really keeping the precision really the same. It was just shifting the exponents up. That's the only thing that I was doing. So far in our experience, it's really exponents that were causing potential challenge. And that's partly the reason why we sort of focus more on FP16 formats, because that gives you more exponent range than, let's say, fixed point representation.
Would it make sense to have a non-IEEE precision format for the
Okay, so yeah, I'll just repeat the question. The question was, does it make sense to have a non-IEEE format? It depends on the definition of what makes sense, right? So IEEE is nice because it's a format supported by various architectures as well as CPU code, right? So if, FP16, there are CPU implementations of that. I think NumPy supports that and so forth. So it makes life easier. If there was a good reason to support something else non-standard, that's substantially better for machine learning, it probably would make sense. And that's partly where we are looking out to the research community to give us some more feedback. I don't have a good answer to that question at the moment.
Okay, if that's with the rest of the questions. Thanks, Pooya.